Can you?
Let me see if I can go full screen. What's wrong now?
You're good. You're good.
Am I good? Am I good? Can you hear me?
Yeah, I can hear you.
Good. Okay. First of all, thank you very much to the NSF for supporting our research. My part of this center will be more on the applied philosophy rather than really hardcore networking. But the philosophy will be applied to networks and everything more than that. And I will describe. Well, we all know AI has been very successful. Take, for instance, ImageNet. ImageNet applied to images does quite, or ResNet applied to images does quite well. A GoogleNet does quite well. But now think about this. You pick up an image that ResNet is confident 57.7%. There's a panda. You add a little bit of noise, and then it is confident 99.3% of the time that it's not a panda. So what's happening here is that this philosophy of classification assumes an IID-ness that I would argue make it less smart than a 2-year-old kid. If you think about a 2-year-old kid, it understands how the nature works without much training indeed, without much data. Somebody said, I want to transfer this scenario of network, I think it was Saman Banerjee, to another scenario, transfer learning. The kid does it without any thinking, without any data. It understands causal effects. So why is it that the AI devices or the current AI situation is not very robust in dealing with non-ID setting? Some group of people say the reason is that it doesn't pay attention to causality. Well, causality by itself is a religion. I remember I listened to a talk by Lutfi Zadeh. He was saying that causality is impossible to verify. So you could think about that because you could say you could never repeat the same experiment. Therefore, it's not going to be the same because it's done another time. So how could you deduce something? But I guess that's against scientific method. So it depends on how you view it, right? But if you could build causality, which you need, if you want to do a self-driving car because you want to do transfer learning on the fly, then you could do many, many things. You go beyond a statistical association, and you will be able to do transfer learning like a kid without much data. I mean, there is transfer learning, there is meta learning. I do love meta learning. And there is the field of lifelong learning, continual learning, all of these things. But they're really toy examples, mainly classification. We want something that does a lot better. So the hope is that causal reasoning can do that, and it can be applied to networks. One thing about causality is that it could be counterfactual. I could say, if I had 2 aspirins before, I wouldn't have a headache right now. But this is not an experiment. This is a counterfactual observation. So if it is the case that I could look at observational data, interventional data, and counterfactual data, what could I do with it? Moreover, if I can understand it well, I would argue that even reinforcement learning will be easier. Because a kid, when it wants to explore, because it knows the causality, it explores efficiently. Why should it be within the framework of random exploration, all kind of things like that, if there is causality there that you understand? How would this causality apply to the AI Center? I think Professor Banerjee pointed out he wants to transfer learning with little data. Cars, driving cars. I mean, if they're self-driving, they better understand what's going on. There was a Tesla running into a truck because it didn't understand causality, right? Self-driving car. This sophistication of networks, hopefully, we'll be able to use these causalities that we'll develop here to perform better in the sense of both at the edge, in the cloud, at observational level, at every level, we need this. So there are different views of causality. Some of them are based on Pearl's doctrine. Essentially, they try to so-called build structural causal models into ML data. These are the group of people that are trying to build this in deep learning. The problem is that if somebody gives you an image or a video, you have to understand what are the important variables in that data. And that is not as easy. Humans know it. I mean, you look at an image, you recognize my face. If the background changes, you recognize me. So what is it that we do that the machines don't do? Okay, so let's talk about this by what we can do and how we can build it into machines, but I better word it that way. In order to put what we are going to do in these 5 years in focus, I want to talk about two kinds of causality. One is the explanational point of view, and the other one is interventional point of view. So there is a group of people, namely people that followed Neyman. Neyman was the guy that first came up with this idea in his master's thesis, and Rubin then further expanded it. They believe that if you cannot change it by intervention, then the causal question is pointless. But there are also a group of people that they believe that by observational data, you can understand what causes what. Some physicists do that too. I mean, they may not be able to intervene in many things, but they like to understand and explain the data, right? So which one of them we are going to do? We are going to do all kinds. We are going to do explanational, interventional, both from Judea Pearl point of view, Rubin's point of view, and beyond. Let me talk about first observational point of view, that you want to explain the data. So let's say you have a bunch of time series, X1 or bunch of images, whatever you like, X1 to Xn, a set of observation. There could be data network traffic. Y1 to Yn, another set of observation. Can we use Y1 to Yn to say they have some value in understanding X1 to Xn? So key to this idea is in the last piece of work that Kolmogorov did in the latest stage of his life. So the idea is that, suppose I tell you, look at everything that you see before time t minus 1, or look at for every t minus 1 data that you have seen. It doesn't need to be over time, it could be over a space. Try to explain the next data point to me. What will be the shortest explanation that you can give? That is given by the conditional Kolmogorov complexity of x of t given x1 to xt minus 1. Now, if you add y1 to yt minus 1 to it, definitely you should be able to come up either with a shorter or at least the same size explanation. If they're totally irrelevant, you just use x1 to xt minus 1. So if you subtract this, what you get is a form of information, which is called Kolmogorov directed information. So let's say this thing has prediction value, causality value, if this Kolmogorov directed information is large. The only problem is that you could come up with cases in Kolmogorov complexity. There's something called, like, for instance, Chaitin's numbers, or Martin-Löf also came up with some sequences that you could not really compute this. They are uncomputable. So therefore you need surrogates. So some people propose to replace Kolmogorov information in this case by replacing K with Shannon entropy. Then you get Shannon directed information. And that is actually proposed by Massey. Jim Massey proposed that. That is computable, but computing entropy from limited observation is notoriously difficult. And now if you assume that there is an AR relationship in the Shannon directed information, all of the data follows an AR model with Gaussian noise, it reduces to so-called, the statistics, essentially this information, reduces to Geringer's causality statistics, the F test. And that's what Granger won a Nobel Prize for, but actually comes from a very special case of Kolmogorov-directed information. So these are the form of causalities that are predictive. The problem is that you have to model them, right? I mean, you have to put the models that are AR models. How do you know it is correct? If you're Granger, that's what you have to do. So you need something that is robust. So here, in a recent work, we showed that actually, if you actually leave Shannonian point of view and go to a Fisher divergence point of view, you will get a new form of information. And this is not like Fisher information. I mean, I call it Fisher inspired, but this is different from Fisher information that is used in Kramer-Rao bound. So, and it's actually presented in this paper down here, I referenced it. So this distribution is a scale invariant. That means that if you pick up the distribution and multiply it by a constant, or in fact, if the distribution is even not integrable, you could calculate this. And we showed robustness of this by using this thing, for instance, to design VAEs, other things that even beat Wasserstein GAN in terms of robustness. So one aspect of it will be if this thing can be used for predictive causality. So I made a toy linear example here. I got data X and Z, and these are the coefficients. So the dimension of X is always 5. Z, the dimension is 15. And when you go to higher dimension, you just add more zeros. And here have a noise that is IID. So the more dimensions of Z you get, it becomes more noise in different coordinates. So what you see that this Fisher method is actually robust to compute. And the confidence interval that there is no predictive causality is beaten even at such a high dimension with such amount of noise. That's the unique robustness of this Fisherian divergence. And it comes from a stability because Fisherian, there is a Stam formula by Stam that actually relates the derivative of mutual information with this Fisher divergence. And that actually is what creates this robustness. So we want to apply this to multiple things. We want to apply this to model selection. We want to apply this Fisherian information to extend it to deep models, develop better understanding of network data. And this is one of the things that we want to do for observational data. Then you take the Judea-Pearl causality. The Judea-Pearl causality is based on assumption that you have a causal graph. This is actually something that you have to figure it out. It's called causal discovery. And the problem is that it depends on conditional independence. Test of independence is notoriously hard with limited data. So here, to choose that Bayesian network, what we are going to do is to use this Fisher divergence for model selection. There has been work on using Shannonian information and BIC, namely Bayesian information criterion. But here we are going to build on these Fisherian techniques that are more robust. Now let's go to the interventional and counterfactual point of view, which is, by the way, all of the people that are proposing to use causality in deep networks, most of them, 99%, are focused on Judea-Pearl's philosophy. The reason is that graphical models have something to do with deep networks. There's a marriage between them, Bayesian neural network, right? But the interventional point of view is just picking up. So because there's limited time, I'm not going to go through the theory, but there are, the way that you want to do this interventional point of view is that you want to get your images or you want to get your videos, come up with a representation learning for these features and understand this interventional causality in the features. So the key to it would be choosing the features. So there's like very little work has been done. There's a lot of talk, but very little work. One of the works that has been done is that people use recurrent neural network in natural language processing. And they got the features and then tried to fit a model between the features, interventions, and factual outcomes. That could be, for instance, a neural network. There's other people that looked at probability of outcomes and interventions given the data, and they modeled it with neural network. So this is just picking it up. But more recently, there has been a nice work by Luizus et al. They come up with so-called a causal effect variational autoencoder that actually enables the inference of counterfactual regret, counterfactual outcomes if the training is accomplished. So what I want to do is apply these to network data and design new causal effect deep networks. This is the architecture.
Oh, Vahid, you got 1 minute.
I am done. I am done.
Okay.
Okay, just give me a second. So what happens is that you got such thing that we are going to extend to other neural networks. And thank you.